Okay, so what we are going to do now is continue with our earlier discussion. So that is about the Noetherian decomposition. Okay, so you see, let me again remind you what we are doing is we have if you remember there is the we took K to be an algebraically closed field, and we took the affine n space over K, which is just Kn with the so called Zariski topology, and what is the Zariski topology? The Zariski topology is the topology for which the closed sets are given by 0 sets of ideals, and the ideals should be taken in the ring of polynomial functions in n variables over K, where the n is the same as this n. Okay, so closed sets are also called as algebraic sets, and they are just of the form Z of I, where I inside the polynomial ring in n variables over K is an ideal. So this is a Zariski topology, and then we have seen that there is a there is already a dictionary between the closed subsets of An and the ideals of the polynomial ring. In fact, if you want a perfect equivalence, a bijective correspondence, then on this side you should take closed subsets of An, on the other side you should take radical ideals in the polynomial ring. Okay, the closed subsets correspond one to one with radical ideals, and this correspondence is inclusion reversing. Okay, and the larger the ideal, the smaller the 0 set of the ideal. Okay, so the 0 set of the ideal is simply the set of points in Kn, the n tuples of points at which every function, every polynomial function in this ideal vanishes. Okay, and now the point is that we defined we checked that this is a topology on this space. Okay, that is, this definition satisfies the axioms for closed sets of a topological space. So An becomes so Kn becomes An with this topology, which is called the Zariski topology, and then I told you that the beautiful thing is that there is a algebraic geometry side, there is a commutative algebra side. The algebraic geometry side is the geometric properties of An and its subsets. The commutative algebraic side is the commutative algebraic properties of the ideals here. Okay, and as a first result, what we showed the last lecture was that the ideal I is prime if and only if or rather the radical of I is prime if and only if Z of I is an irreducible closed subset. Okay, so here when we defined irreducibility, if you recall, irreducibility was a strong form of connectivity. Okay, and whereas for a set to be connected you require that it cannot be written as a disjoint union of two proper non-empty closed subsets. The condition for a set to be irreducible is much more stronger. The condition is that it cannot be written as a union, not necessarily disjoint, but of proper non-empty closed subsets. Okay, so an irreducible set is of course connected, but the converse is not true, and irreducible sets satisfy all the nice properties that you similar properties as connected sets. Okay, and so the point was that we called irreducible closed subsets of An as affine varieties in An. Okay, and so let me write that irreducible closed subsets of An are called affine varieties in An. Okay, and so the point is so of course the advantage of studying an irreducible closed set is that you have the additional property that it is irreducible. Okay, and this irreducibility is a topologically a very nice property. It's a property that's really nice in the sense that, as I told you last time, for example you can define irreducibility for any subset of a topological space. First of all, it's not necessary that you should define it only for closed subsets, and the point is that if you define irreducibility for any subset, you will have to make the definition with respect to the induced topology. So you should say that the subset cannot be written as a union of proper non-empty closed subsets closed for the induced topology on the subset induced from the bigger topological space in which the subset is sitting. Okay, and the advantage of irreducibility is that so let me mention some of them. Well, if a subset is irreducible, then its closure is also irreducible. So adding the boundary, which is the same as taking the closure, is not going to take away the irreducibility. Then if you take a non-empty irreducible set, of course we by definition we always require that an irreducible set is non-empty because we declare the null set not to be irreducible. Okay, so well an irreducible set if it is non-empty, then it has a nice property that every open non-empty open subset is dense. Okay, and every non-empty open subset is also irreducible. Therefore, you know, in an irreducible space a non-empty open subset is enough to test all properties of the space which are going to be preserved when you take closures, that is when you take limits. Okay, so it's very important to be able to test on a non-empty open set. Okay, and non-empty open sets are irreducible for an irreducible space. Okay, that's one nice thing. Then the other nice thing is of course that any non-empty any two non-empty open sets will intersect. Okay, that will tell you that the topology is not housed off. Okay, when compared to the usual topology. For example, if you take k to be complex numbers, okay, then the an c, which is c to the n, c cross c cross c, n dimensional complex space, n dimensional thought of as a vector space, Cn is with the Zariski topology is not housed off. Okay, that's because of this reason, because it's irreducible and the whole space is always irreducible. Please remember that's because this corresponds to the zero ideal, and the zero ideal the zero set of the zero ideal is the whole space, and the zero ideal is of course prime because zero ideal is an ideal in an integral domain. Okay, in a commutative ring with unity which is an integral domain, the zero I mean if you take a commutative ring with unity, the zero ideal is prime if and only if the ring is an integral domain. Okay, so this is always reducible. Okay, so any two open subsets of this will always intersect, so it's highly non-housed off. Okay, housed offness means that you give me any 2 points, you can find open sets small enough such that they contain those 2 points and they don't intersect. So this is highly non-house stuff, but still that doesn't deter us from doing good geometry. Okay, that's the point. And well, so, and of course there are other nice things. For example, the continuous image of an irreducible set is again irreducible. This is proved in exactly the same way as you prove that the continuous image of a connected set is connected. Okay, so studying irreducible closed sets is of course very nice, and of course from the geometric point of view it's very nice, and from the algebraic point of from the commutative algebraic point of view also it's very nice because you're studying prime ideals. Okay, but then the point is, how do you get to an arbitrary closed set? How do you study an arbitrary algebraic set? Okay, so the fact is that the answer to that is that these irreducible closed subsets, which are the affine varieties, they are the building blocks for the algebraic sets. So there is something called the Noetherian decomposition theorem, which says that any algebraic set, any closed set in AN, affine n space over K, is writable as a union, a finite union of irreducible closed subsets, namely affine varieties, and the union is and this decomposition is unique, and if you assume that there are no redundancies, that means that there is no component which is containing some other component in the union. Okay, so now how do you prove that? The answer to proving such a theorem is the Noetherian property. Okay, so last time I defined what is meant by Noetherian. So AN K is a Noetherian topological space. So let me quickly recall this. So again let me tell you the reason. One reason for this Noetherian condition is to be able to say that any algebraic set can be broken down into a finite union of affine varieties, and the finite union is, this decomposition is unique if you assume that there are no repetitions in the union. Okay, of course unique up to permutation of the pieces that occur. Okay, so if you want to study any algebraic set, all since you can break it down as a union of varieties, it's just enough to study varieties, and that's why we study only varieties. Okay, that gives us some justification as to why to study varieties and not just algebraic sets. That's part of the reason why at least in a first course in algebraic geometry we study only affine varieties, and I mean we study affine varieties to begin with, and then probably study projective varieties, but we don't study non-irreducible closed sets. Okay, we study only irreducible closed subsets because general non-irreducible closed set can always be broken down like this. So the key to showing that any algebraic set can be broken down into a finite union of affine varieties in a unique way is due to the fact that AN is a Noetherian topological space. So let me recall what I told you in the last lecture. See, the Noetherianness of a topological space is the condition that the closed subsets of the topological space satisfy the so called descending chain condition. That is, if you give me a descending chain of closed subsets, each one containing the next one, okay, so the closed sets are becoming smaller and smaller and smaller, then such a chain has to become stationary at some point, that it has to become stable. That means beyond a certain point all the sets occurring in that chain in the sequence, they all have to be one and the same. Another way of saying it is that if you take a descending chain of closed subsets such that at every step it's a proper containment, okay, that means it's a strictly descending chain of closed subsets, then that has to be only finite. You cannot have an infinitely you cannot have an infinite chain of closed subsets which are becoming smaller and smaller, strictly smaller one after the other. Okay, so this is the descending chain condition for closed subsets, and this condition translates into the ascending chain condition for ideals in this polynomial ring. That's because after all the closed subsets in the affine space are they correspond to ideals in the polynomial ring, okay. And in fact if you want exact correspondence you have to worry about radical ideals, okay. But the fact is that if you give me any ascending and because the correspondence between the closed subsets of an and the ideals in the polynomial ring is the inclusion reversing correspondence, the descending chain condition for closed subsets in the affine space will translate to an ascending chain condition on the ideals in the polynomial ring. And but the polynomial ring does have the ascending chain condition on ideals because it's a Noetherian ring. So you see one of the definitions of a Noetherian ring is that the standard definition is always that it satisfies the ascending chain condition for ideals. So that is, in other words, if you have a sequence of ideals becoming larger and larger and larger, every ideal being contained in the next one after it, then that has to stop at some stage. It has to either become stationary or another which means that beyond a certain stage all the ideals should be one and the same in the sequence. The other way of saying it is that if you have a strictly increasing chain of ideals, then it has to be just finite. You cannot find an infinite sequence of ideals which are becoming bigger and bigger and strictly bigger and bigger and with this whole thing never coming to an end. This cannot happen in a Noetherian ring. So the fact is that this is equivalent to the fact that the polynomial ring in n variables is a Noetherian ring. And why is the polynomial ring in n variables over K a Noetherian ring, and that's just because of Hilbert's basis theorem. That's just Emmy-Noether's theorem, which says that if you start with the commutative ring with 1, if that commutative ring is with 1 is Noetherian, that is for example if it satisfies the ascending chain condition on ideals, then so does the polynomial ring in n variables over that ring, okay. Now a field is always Noetherian because a field has only 2 ideals. One is a 0 ideal, the other one is a full field which is a unit ideal, and therefore a field is always Noetherian, and therefore if you use Hilbert's basis theorem, if you take a polynomial ring in finitely many variables over a field, then that will also be Noetherian, and that's the reason why this is Noetherian. So you see the topological side, on the topological side the space an is Noetherian, and on the commutative that is on the algebraic geometric side at the level of topology the affine space is Noetherian for the Zariski topology, and in the commutative algebra side the ring of functions on affine space, namely the polynomial ring, that is a Noetherian ring, and these just correspond to each other, okay. Now I was trying to so I stated a theorem. So this is a theorem that will let us to prove that any algebraic set can be decomposed into a union of affine varieties, okay. So let me recall that theorem and let me try to prove it. So here is a theorem. If X is a Noetherian topological space, then any closed subset, any non-empty closed subset y of x can be written uniquely, I should say can be written, let me explain what uniquely means, rather can be written as y equal to y1 union ys, okay, with yi irreducible closed non-empty and this decomposition is unique up to a permutation of the yi's if no yi is a subset of some yj for j not equal to I. Okay. So any non-empty closed subset can be written as a finite union of irreducible closed non-empty subsets. Okay, so each of these is irreducible, it's closed, it's non-empty, and this decomposition is called, you can make it unique if you make sure that you don't have redundancies. Okay, so for example, if y1 is, if you have y1 union y2 and so on, and if y1 is contained in y2, then why put y1, you can throw out y1 because it's already there in y2. So once you can write a decomposition like this, you can always throw out some of them which are contained in the others, and finally you can arrive at a decomposition in which none of the sets is contained in the others, in any of the others. Such a decomposition is unique. Okay, such a decomposition is unique, and that decomposition is what is called as a Noetherian decomposition. Okay, now and the yi's are called the irreducible components of y. Okay, so each yi is called an irreducible component of y. Okay, so the decomposition, this decomposition such a decomposition is called a Noetherian decomposition, and the yi are called the irreducible components. They are called the irreducible components of y. It is much similar to what you do in topology. You take any, in topology you define connectedness of a subset, okay, and then you prove that any topological space can be written as a union of its connected components. Okay, in the same way, here you are saying that any topological space, if you want any topological space to be written as a union of its irreducible components, and you want that to be a finite union, the condition you have to put on the topological space is that it should be Noetherian. Okay, that is a nice condition, and that condition is there for us for the affine space, as we have already seen. So if you believe this theorem, you will immediately get that any algebraic set can be uniquely decomposed into affine varieties in this sense. Okay, so that proves the statement that we want. All right, so you have to prove, we want to prove this. It's pretty easy to prove. So the point I want to say is that here we are going to use the various other definitions of Noetherianness of a topological space. So you know, the original for example, if you take as starting point the definition of a Noetherian topological space, that there is DCC for closed subsets, that is there is you cannot have a strictly decreasing sequence of closed subsets, one containing the next, which is infinite. Okay, then this is equivalent to also saying that any non-empty collection of closed subsets has a minimal element. Okay, and that is also equivalent to saying that any non-empty collection of open subsets has a maximal element, because the open subset is just, you know, complements of closed subsets in any topological space. So you know, so DCC for closed sets is the same as ACC for open subsets, and DCC for closed subsets is the same as saying that any non-empty family of closed subsets has a minimal element, and that is equivalent to saying that any non-empty family of open subsets has a maximal element. So these are all various avatars of the definition of the Noetherianness of a topological space. Okay, and it is not surprising, because if you have seen this in commutative algebra or in algebra, you know that there are also several ways of defining a ring to be Noetherian. One, of course, a standard way is to say that you know, it has ascending chain condition for ideals. Okay, but then there are other equivalent conditions. The other useful equivalent conditions are that every ideal is finitely generated, okay, which is also a very important condition, and the yet another condition is that given any non-empty collection of ideals, there is always a maximal element, maximal with respect to inclusion, okay. So whenever we say maximal, it's always, if nothing is mentioned, maximality is always with respect to inclusion as subsets, okay. And of course, you know, the each one has its own, each of these axioms has its own importance. See, for example, while the ascending chain condition on ideals gives rise to the descending chain condition for closed sets, the fact that every ideal is finitely generated is also very important, because that's what tells you that if you take any ideal, okay, any ideal, mind you, if you take any ideal and look at the zero sets okay, if you use the fact that Noetherianness means that every ideal is finitely generated, it will tell you that whenever you are looking at the zero set of an ideal, you are just looking at the common zeros of a bunch of finitely many polynomials. So you are not, an ideal is always, a non-zero ideal is always going to be infinite, okay, there are going to be infinitely many elements in it, okay. So the point is that it looks like when I take the zero set of an ideal, namely all the points in the affine space which at which every one of the functions the ideal vanish, it looks like I am solving too many equations, okay, but it's not true. In fact, you're trying to find common zeros of infinitely many equations, okay, but that's not really true. What is really happening is that you are only finding the set of common zeros of only finitely many equations. And why finitely many? Because those will be those finitely many equations, for example, which generate this ideal, and that's true because the ideal is an ideal of a Noetherian ring and it is finitely generated. So you are always looking at only common zeros of only finitely many polynomials, and this finiteness is very important because it allows you to do, for example, calculations on the computer. So if you have if I want to look at the zero set of an ideal, then you know I look at zero sets, I take the generators of the ideal and I first look at the zero sets of the first generator and then intersect it with the zeros of the second generator and go on, and I can have to do this process only finitely many times, okay. So that's the reason why you can do computational commutative algebra, which will help in algebraic geometry, okay. So anyway, so let me come back. So the point is that the property for Noetherianness of the Noetherian hypothesis on the topological space I am going to use is not it's not ACC on closed subsets that I am going to not DCC on closed subsets that I am going to use, but what I am going to use is I am going to use the other equivalent definition that any non-empty family of closed subsets has a minimal element, okay. So that's what I am going to use, okay. So let us see how to use it. So it's a very simple argument. So what you do is basically you assume that there are so you try to contradict this statement, okay. So what you try to say is you assume that there is a subset which cannot be written as a finite union of irreducible closed subsets, okay, and that's a specimen because that's something that contradicts this theorem, okay. The point is that you should not show that you should show that there is not even a single one like that, okay. Now the point is what you do is you put all these specimens together in a subset and apply the existence of a minimal element for that subset, okay. That's the whole point. So what you do is so let me write this. Let if possible let S script S in be the collection of closed subsets of X that cannot be written as a finite union of irreducible closed subsets okay. If possible, let script S be the collection of closed subsets of X that cannot be written as a finite union of irreducible closed subsets and S non-empty. So that means you have to show that this collection script S is empty, namely you should show that there is no closed subset that cannot be written as a finite union of irreducible closed subsets. So you go by contradiction. What you do is you take script S to be a non-empty collection of closed subsets which have a property which contradicts the property of the theorem. Not even the stronger uniqueness of decomposition, it contradicts even the existence of decomposition. Okay, so S is non-empty. Now after all, S is just a collection of closed subsets of the topological space X, and X is Noetherian. But you know, Noetherian, one equivalent definition of the Noetherian condition is that given any non-empty collection of closed subsets, it will always have a minimal element. Okay, so since X is Noetherian, S has a minimal element say y0. So there is a, so y0 is a kind of smallest kind of subset, irreducible, I mean smallest kind of it's a closed, of course non-empty closed subsets. You will have to, I mean you will have to be careful about this. It should be non-empty closed. Okay, because of course this decomposition is only being made for a non-empty closed set. Okay, so there is a minimal element, which means that y0 is a non-empty closed subset. Y0 cannot be written as the union of proper closed subsets, and it is the smallest in the collection S, smallest with respect to what? With respect to inclusion of subsets, which means that if there is an element of S which contains y0, I mean if there is an element of S which is contained in y0, then it has to be equal to y0. That is what minimality means. Minimality means that if there is some other thing which is smaller than this, then it has to be this. Okay, fine. Now you watch carefully. Since y0 is in S, the first observation is y0 is not irreducible. Okay, see, because if y0 is irreducible, then y0 can be written as y0. The fact that it cannot be written as a finite union of irreducible closed sets tells you that it cannot itself be irreducible, because if it is irreducible then it is itself. When I say union, this union can be just one. Okay, so what you must understand is the elements of the script S by definition they are all not irreducible. So what happens is y0 is not irreducible. Okay, note that y0 is not irreducible. Y0 is not irreducible. Okay, now but then what does it mean? Y0 can be broken down into two as a union of two proper non-empty closed subsets. Okay, so y0, so let me continue here. So y0 is equal to y01 union y02, where y01 y02 are proper non-empty closed subsets of y0. Okay, y0 is not irreducible, so it is reducible, so it can be broken down as a union of two proper non-empty closed subsets. But now watch, y01 is a closed set which is smaller than y0, and y02 is also smaller than y0. So y01 and y02 cannot belong to script S. See, y01 is a proper subset of y0 and it is a non-empty closed set, and y02 is also similarly a non-empty proper closed subset of y0. So these two closed subsets cannot belong to script S, because if they belong to script S they will contradict the minimality of y0. Y0 is supposed to be the smallest. Okay, so the fact that y01 and y02 do not belong to script S means that they can be written as a finite union of irreducible closed sets, and if that is true then y0 also can be written as a finite union of irreducible closed sets, namely you just take the union of the irreducible closed sets, the finite union of irreducible closed sets that gives y01, and take also the finite union of irreducible closed sets that gives y02, put them together, that will tell you that y0 becomes writable as a finite union of irreducible closed subsets, but that is not possible because y0 is supposed to be in script s. So this contradiction tells you that script s has to be empty, and this argument finally tells you that every closed subset, non-empty closed subset, is necessarily writable. It can necessarily be broken down into finitely many irreducible closed subsets. Okay, so this gives you the existence of a decomposition, not without the uniqueness. We will get the uniqueness next. Okay, so let me write that down. Since y01, y02 are proper closed subsets of y0, y01, y02 do not belong to the collection, but then y01 and y02, and hence y0 is writable as a union of non-empty, of finitely many non-empty irreducible closed subsets, which contradicts y0 belongs to the family. Thus the family is empty. In other words, every non-empty closed subset is certainly writable as a union like this of non-empty proper of non-empty irreducible closed subsets. Okay. So thus any non-empty non-empty closed subset y can be written as y equal to y1 ys with every yi non-empty closed irreducible. Of course, whenever I say irreducible, it's automatic that it's non-empty, because we have barred the null set from being taken as irreducible. Okay. So now of course if some yi is contained in some other yj, you can throw the yi out. So you can assume without loss of generality that no yi is contained in any other yj. Okay, and then what the theorem says is that with that assumption this decomposition is unique. That is what we are going to prove next. Okay, so if some yi is contained in another in yj for j not equal to I, we can exclude that yi from the union. Thus we may assume that yi is not contained in yj for I not equal to j. That is the union is not redundant. Okay, this you can assume, is obvious. The point is that once you assume that, this decomposition becomes unique. Okay, that is what we are going to prove next. So let me do that. So let me write that down. Uniqueness of decomposition So let me write a lemma. I will use a small lemma. If Z is contained in Z1 union Z2 union ZR, where Z is irreducible, then Z is contained in Zi for some I. Just a moment. I will also need that all the Zi's are. Let me assume that Z is. Let me assume Z is closed and all the Zi's are also closed. Where Z I are closed and Z is reducible, then Z is contained in Zi for some I. That's correct. Yeah. So if you have a irreducible, if you have a union of closed sets, finite union of closed sets, and if there is a set which is contained in irreducible set which is contained in the finite union of closed sets, okay, then if it is irreducible, it has to go into one of them. Okay. So the proof is, well, you see, I mean, you just have to use the see the condition, the condition given means that that Z is actually, you know, Z intersection Z1 union Z intersection Z2 union Z intersection Zr, okay, because if you intersect Z is contained in this union, so Z intersect that union is Z, but Z intersect that union is just Z intersect each member of the union and then you take the union. So because the intersection distributes over the union, okay, so that's what it means. And notice that each Z intersection, see since Zi are closed in the ambient topological space, the big topological space, therefore Z intersection Zi is closed in Z, okay. So the each Z intersection Zi is closed in Z, okay, that's very clear, because that's what induced topology means. Induced topology means, induced topology in a subset is that a subset of that subset is closed if that subset which you are claiming to be closed is gotten by intersecting with a closed set in the bigger space, okay. So Z1, any Zi is closed in the big topological space, therefore its intersection with a subset is closed in that subset, okay, fine. Then the other thing is that, of course, you know, I can, in this union I can simply forget if some Z intersection Zi is empty, okay. So if some Z intersection Zi is empty, I do not write it at all, so I can assume no Z intersection Zi is empty, or rather is non-empty for every I, okay. I mean, if it is empty, just forget that index and re-index, you will get a lesser number of indices, okay. So after this assumption maybe this R will come down, it might come down to a smaller number, okay, but let us not, it's not really, one is not really worried about what that smaller number is, one is only worried about that it's the fact that it's finite, okay. Then the other thing that you must understand is, if some Z intersection, so you see, if some Z intersection Zi is equal to z, then we are done, because if some z intersection zi is z, then you are just saying that z is contained in zi, alright. So we are done. Okay, z is contained in zi, alright. So if some z intersection zi is equal to z, then you are done. Okay, if not, if suppose z intersection zi is properly contained in z for all I, this is the other possibility. We have to show that this possibility does not occur. Okay, we have to show that this possibility does not occur, and the only possibility that occurs is z intersection zi is z for some I, and therefore z is contained in zi for some I. That's essentially the lemma. Okay, now suppose z intersection zi is proper subset of z, so what it will tell you is that you have broken down z into a finite union of non-empty proper closed subsets. Now that's not possible, because z is that's because z is irreducible. Okay, the irreducibility says that you cannot break it down into a union of two proper non-empty closed subsets, but you can extend it to finitely many. The reason is because you see, suppose I have this condition, what I can assume is that I can also assume that z is not contained in any union of a sub collection of the zi's. Okay, so in other words I am saying that you can also assume without loss of generality that you know z is not in the union of say for example you throw out z1, it is not in this union because if it is in this union I would work with this. So try to make sure that z is not contained in any smaller union, a union of a subset, proper subset of the collection of all the zi's. You can assume that. Okay, assume that z we can assume so let me rewrite this. We may assume that z is not contained in zi1 union zi L for a subset, a proper subset I1 etc. IL of 1 2 etc. R. You assume that. Okay, so you can assume that. Otherwise, if there is something like this, then work with this, call this subset as 1 through, replace this collection with that subset, and what you will do is you will keep on reducing to a stage until you will come to a point where you get a collection like this. Okay, that is z is contained in the union. Okay, z intersection zi is a proper subset of z for every I, and z is not contained in any smaller union. You will come to a stage like that. Okay, now you have to say that is not possible. You see, then you will have z is equal to z union z1 union z union z2 z union zr. I will break it down like this. See, this is non-empty closed proper. Okay, and this guy oh sorry, these are all intersections. I am a little careless. Yeah, so this is, if you look at it, both of these guys here are non-empty closed proper. So what I have done is I have broken an irreducible set into two pieces, which each of which is non-empty closed proper. that is a contradiction to the irreducibility of Z. So this can never happen. Therefore the only thing that can happen is that Z has to be in Zi for some I. Okay, so this implies Ez not irreducible, and that implies that implies a contradiction, which proves the lemma. So your lemma is proved. So the moral of the lemma is that if an irreducible set is contained in a union of finite union of closed sets, it has to go into one of them. In other words, it cannot fall into two pieces in a union, it has to go exactly into one of them. Okay, now let's apply that to the uniqueness of decomposition. So let me go back here. Okay, so let me go back here. Now assume, now let y equal to y1 union etc ys, and let that also equal to y1 prime union y prime s prime with every yi y prime j irreducible closed, of course non-empty. Okay, what do you have to prove? You have to prove that S is equal to S prime, and you have to prove that every yi is some y prime j for a unique j. Okay, so of course you know and of course you are assuming that there are no redundancies. Yi is not contained in yj for I not equal to j, y prime y prime I is not contained in y prime j for I not equal to j, where of course here the ij's are indices from 1 to s prime, and here the ij's are indices from 1 to s. Okay, that is to show S equal to S prime, and each yi is precisely some y prime j. Okay, that is what you have to show. So and how do you do that? It's very simple. You see, so let me first state it in words. I am going to use that lemma. Take y1. Now y1 is a sub of this union, so it is a sub of this union. Okay, now the lemma says that the set y1, I don't need the fact that y1 is closed, I only need the fact that y1 is irreducible. y1 is contained in a union of finite union of closed sets, therefore it has to be in exactly one of them. It is contained in at least one of them, not exactly, it is contained in at least one of them. So if I apply the lemma, I will get that y1 is contained in some y prime j. Okay, now again apply the lemma to y prime j, that y prime j is contained in all the union of the yi's, and that y prime j is irreducible, therefore y prime j is contained in some y j prime. Okay, so if you write this down, you will get that y1 is equal to y prime j, you will get y1 is equal to y prime j. So so let me write that, since y1 is contained in the union of yi primes, we have by the lemma, just using the fact that y1 is irreducible, that y1 is contained in y prime j for some j. Okay, similarly, since y prime j is contained in the union of yi's, we have, since y prime j is irreducible, that y prime j is contained in some y, I don't want to use k, but let me use L if you want. Okay, so you will get y1 is contained in y prime j, which is contained in yl. Okay, so finally you get y1 is contained in yl, but you are not supposed to have that, because the y's are all they are non-redundant, none of them is contained in the others. So what this will tell you is that L equal to 1, L has to be 1, and that will tell you that y1 is equal to y prime j. This implies L equal to 1, that is y1 is equal to y prime j. Okay, now the point is you renumber all these, okay, you renumber all these guys so that you call that y prime j, call that as y prime 1, and the fact is that you can now strike off from the union the y1 and the y prime 1. The fact that you can strike off uses this topological fact that any non-empty subset of a irreducible set is dense. Okay, so I mean the fact is that if you take this union, okay, and you throw out y1, okay, you will get an open set, because what you have thrown out is a closed subset. Okay, because you are taking a complement. If you removing y1 from this union is like taking the complement of y1 in y, that is a complement of a closed set. Okay, so it is open, but it is not if it is non-empty, then it is dense. So if I take y1 out and take the closure, I will get the union of the other pieces, because what I have taken out when I take y1 out from y, I am taking out also y1 from y2 through ys. Okay, so what I will get is essentially a subset of y through to ys. Okay, and what I have thrown out from each of the y2 to ys is a closed subset, it is a proper closed subset. Okay, therefore whatever that is left out, if I close it up, I will get back y2 through ys. So in other words, from this union, if I take out y1 and if I close it up, what I will get is y through to ys. So this is, you can think of this as a cancellation property. Okay, so well, so let me write that, or rather that leads to a cancellation property. So let me write that out, it's just a couple of more lines, then we can wind up. So let me write that down. Renumber, relabel or reindex the y prime j, the y prime l, so that y prime j is y prime 1. Okay, that y prime j which we got to be equal to y1, call that as y prime 1, renumber it. Okay, then y is equal to y1 union y2 union ys, and that is also equal to y1 prime union y2 prime union y prime s prime. Okay, and you know the point is that this is the same as y1, is equal to y1. This is y1. Okay, and now what I want to say is that if you, I want to say that this implies that y2 union ys is actually equal to y1, I mean y2 prime union y prime s prime, which is like you cancel off the y1 that is on both sides of the union, and this cancellation property is actually because of the irreducibility property. Okay, that any non-empty open subset of an irreducible space is dense and in fact actually this is equal to y minus y1 closure. In fact, you take this union, from that union you remove y1. Okay, what you get will be an open subset of y through to ys, and it is a non-empty open subset of y through to ys, therefore if its closure will be y through to ys. Okay, because in each piece the elements, for example in y2 that you have removed which are common with y1, you will get an open subset of y2. If I close that up I will get my y2 back. That is because this open subset that I have removed, I mean this closed subset that I have removed is the common elements between y1 and y2, and that is not the whole of y2 because no yi is contained in some other yj. So if I remove y1 from y2 and close it up I will get back y2. So in the same way from this whole thing, if I remove y1 which is equivalent to removing the intersection of y1 with each of these pieces and then close it up, I will just get the union of these the other pieces. And now what you can do is you can continue the induction. You can next strike off y2 and y2 prime, okay. I mean you can strike off y2 and some other y prime j, okay, because they will be equal by the same argument, and that y prime j can be re-indexed so that you get that y prime j becomes y prime 2, okay. Then you can strike that off and you can keep on doing this, and this process has to end finitely, and when it ends you can't, this s has to be equal to s prime, because if it isn't, if s is less than s prime, then at some point you will get a null set here equal to a set there which is not empty, and if s is greater than s prime, at some point you will get a null set on the right side which is equal to a non-empty set on the left side. So this argument can go on, it can go on only finitely many times, and the fact that you cannot have a non-empty set equal to an empty set, it will force that s has to be equal to s prime, and every yi is unique yj, y prime j, okay. So continuing as before, we find that y2 is equal to y prime j for some j, renumber, reindex y prime j as y prime 2, and we get after cancelling of y prime 2 that you will get y3 union ys is equal to y prime 3 union y prime s, y prime s prime, and by induction we will end with s equal to s prime and ys equal to y s prime, okay. That will be the end of the proof, okay. So finally you get this uniqueness of decomposition, okay. So the moral of the story is that uniqueness of decomposition and the Noetherian decomposition itself holds for a Noetherian topological space, and the nice thing is that it holds for a affine space, and therefore any irreducible any closed subset of affine space, namely any algebraic set, is a finite union of affine varieties, and these affine varieties are unique if you assume that the union is non-redundant, that is none of them is contained in any of the other, and this is called the Noetherian decomposition of a closed subset, okay. So this tells you partly why it is worthwhile to study affine varieties rather than just studying algebraic sets, because the affine varieties are building blocks for any algebraic set can be decomposed into affine varieties. So the affine varieties are the building blocks for our algebraic sets, and in fact it is true also in the widest generality of algebraic geometry, in the most sophisticated language of algebraic geometry. It is the affine pieces that are the building blocks. The most general object in algebraic geometry, the most sophisticated object, is called a scheme, and the definition is that it is built up by the building blocks which are called affine schemes, and this is the philosophy. The affines are like the bricks that make up the whole building, okay. They are the building blocks, okay. So I will stop here.